Hello everyone, I'm Paul and today we're solving problem 1277, count squares and matrices with all ones. This is medium and the key to solve this is dynamic programming. So let's start. We are given a matrix of ones and zeros and we need to return the number of squares and matrices with all ones. So for example, here we have a square with all ones. This is also a valid square, this is valid, and every square here is also valid. So at least we know we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares. Now we also know that this is a valid square, this is valid, this is valid, and this is valid. So here we have 4 more squares. And we also know that this big square is also valid. So in total, we have 15 valid squares. So we return this number. Now let's think in small terms here. Let's say we are standing here in this square. We know that from here, we have at least one valid square because this is a 1. And from here, we have the perfect view to check if this is also a valid square. Why? Well, because these 3 elements are adjacent. They are right next to the current element. And given that every value here is a 1, we know that this square is also valid. Now let's say for a moment that we already know that this is a valid square. And from here we have the perfect view to check if this is also a valid square. Why? Well, because every element here is adjacent to this square. And given that every element is a 1, we know that this is also a valid square. And in case you didn't notice, this looks a lot like a DP grid, dynamic programming. And actually we are using this exact matrix as our DP grid. And each value here will be the count of valid squares which have the current value as the bottom right corner. So here we have 1, 2, 3. So in this case, the value for this cell will be 3. So with this in mind, let's go from the start. First we are here, and given that this is a 0, this is not a valid square. Now we are here, and we know that this is a valid square because we have a 1. And we can't check if this is a valid square because these 2 cells are out of bounds. So we continue with the next cell. Here we have another valid square. This is another valid square. Next we are here. This is a valid square and we can't check if this is a valid square because these 2 cells are out of bounds. So we keep a 1 here. Now we are here. This is a valid square and we can check if this is also a valid square or not. In this case, it's not because this is a 0. So we keep a 1 here and we continue. Next we are here. We know that we have at least one valid square in this cell. And now we can check if this is also a valid square or not. In this case, it is because every value next to the current value is greater than 0. So now we know that from this cell we have 2 valid squares. Next we are here, so we know we have at least one valid square from this cell. And we can check if this is also a valid square. Given that every neighbor is greater than 0, we know we can add valid squares here. Now the question is how many should we add? Because here we have a 2 and these 2 values are 1. The answer is we need to add the minimum among these 3 values. The minimum value here is 1, so this is now 2. Next we are here, this is a 0, so we continue. Next we are here. We have one valid square here, and we can check if this is also a valid square or not. In this case, it's not because we have a 0 here. So we can just take the minimum among these 3 neighbors, which is 0, and we add a 0 here and we continue. Next we are here, this is a valid square and we are checking if this is also a valid square. In this case it is. We take the minimum among these 3 neighbors, which is 1, and add this to the current value, so this is now 2. Finally, we are here. So we are checking if this is a valid square, and it is. So we take the minimum among these three neighbors, which is 2, and add 2 here. So this is now 3. And remember what this 3 represents is this is a valid square, this is also a valid square, and this is also a valid square. Remember that here we are carrying results from previous squares. So by the time we reach this cell and we check our neighbors, we are already considering previous results for previous squares. So this is how we can get a 3 in this cell. Meaning just by considering the current neighbors, we are also considering these neighbors that are not right next to the current value. So finally, we need to return the number of valid squares, meaning squares with all ones. And the answer is the sum for every value here. 1 plus 1 plus 1 is 3, plus 2 is 5, plus 4 is 9, plus 1 10, plus 5 15. So we return 15. Time complexity for this will be big O of n times m. And this is fine because n is roughly 300 and m is roughly 300. And we can handle 300 square. Space complexity will be big O of 1. So now let's go with the code and hopefully you will get the idea. First we say n is the length of matrix, m is the length of matrix 0, and result is 0. And now we can say for I in range n, for j in range m, and if the current cell, the current value is a square, if matrix I j is 1, we can check if we can form a square, another square with our neighbors. And for this, first we need to check if the current neighbors are inbounds. So if I is greater than 0 and j is greater than 0, we can add to the current value matrix I j plus equal the minimum among every neighbor, meaning matrix I j minus 1, matrix I minus 1, j minus 1, matrix I minus 1, j. And every time we need to add to the result the current value, matrix I, j. So finally we can return result. This is it for the code. Now let's submit this and see if it works. As you can see, this works and it's very efficient. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.